So we talked last day about Michael Faraday, one of my nerd heroes, the father of electricity and magnetism. Basically, most of our discoveries come from him. He was the one who gave us these pictures of electric field lines. Let me tell you a little bit about how we interpret these. How many lines does this charge have? Count them. How many lines does this charge have? We would say we know that these two charges have the same magnitude. I'm not saying they're 8 coulombs, Alex. I am saying if two charges have the same number of lines, you can assume they're the same size. One's positive, one's negative, but same magnitude. If this was 0.2 coulombs, this is negative 0.2 coulombs. If this is 1 microcoulomb, this is negative 1 microcoulomb. So if this had 16 lines, I could safely assume this charge was twice as big as this one. I won't test you on that, but I'll use pictures kind of like that. So you'll say, how come this one has more lines on it? Bigger charge. How come this one has fewer lines on it? Smaller charge. Secondly, how close the lines are together, that kind of illustrates the strength of the electric field. The electric field in location 1 is much stronger than the electric field in location 2 because the lines there are that far apart, the lines there are that far apart. Well, you know what? That makes sense because our equation for calculating electric field was KQ over R squared. Look, as you go further away, electric field gets smaller, and in fact, it's that inverse square law. If you go twice as far away, it's 4 times weaker. You might recall we looked at it in the gravity equation when I had 2 people and I played some music and I had them coming closer and moving further away, and we figured out what the mathematical relationship was. Okay? Here's a better picture of 2 oppositely but identically magnitude charges. Opposite charges but the same size. So we kind of tried to sketch one right here in red. That's a much better picture. You can see, now here's a question you will see in your future. In fact, this will be a multiple choice question. I'll probably give you a picture that looks something like this. And in multiple choice, I'll say, is the left-hand charge positive, right-hand charge positive, left-hand choice negative, left-hand charge negative, right-hand charge positive, negative, negative, positive, negative. There's my 4 options, and I'll ask you to pick the correct one. How could you figure out which charge was negative and which charge was positive? Yeah. Yeah. Okay. So I'll give you something like that, or I'll give you something like that. And the arrows might be going towards, the arrows might be going away, and I'll ask you to tell me what the polarity of the charges are. That's a classic, just conceptual, nice little multiple choice question. Example 9, I like example 9, I like example 9. Example 9 is a nice question. Zaina, what does example 9 want me to find? Okay. There's a couple of issues here. Say it again, you're correct. What does it want me to find? The electric what? What letter does field begin with? The letter F? I see a lot of kids, don't write this down, they'll start finding the electric force because, well, that's an F, Mr. And unfortunately, I have to give them 0. We experienced a similar thing on the test we just wrote on gravitation. We haven't gone over it yet because there's still a bunch of people left to write. But a number of you, when I asked you to find the gravitational field near a black hole, you found the gravitational force near a black hole. And unfortunately, I had to give you a 0 because you may have done it right. Thank you, but not what I asked for. It's like if I asked you to find the acceleration and you find the time. Again, well done. Just not what I asked for. So this is where our running out of letters is kind of going to come to bite us a little bit. So again, what does it want me to find? What letter do we use as our abbrev for electric field? Capital letter E. Okay. I'm going to number the... They numbered the charges for me. Thank you. What I'm going to do to find the overlapping electric field right here, Maddie, I'm going to find the electric field from charge 1, magnitude and direction. I'll find the electric field from charge 2, magnitude and direction. Then, Nick, I'll find the electric field from charge 3 at that location, magnitude and direction, and then I'll add them vectorially. Are they all in a nice straight line, Nick? So I don't need to worry about tip to tail. I'll use winner minus loser. I'll figure out which is the bigger one. I'll call one direction positive, one direction negative. Okay? So, Nick, what is my electric field equation? I'm going to write E1 for charge 1, just to be lazy but organized. What is my electric field equation, my friend? So this will be KQ1 over R1 squared. Little k acted like big G. It was the number that had to go in our equations so that we got answers in newtons. What was little k? You might have memorized it already, but otherwise it's on your formula sheet. Worth memorizing that one out of laziness because it's a pretty easy one. 9, right? Also, you'll notice much nicer to type than 6.67 times 10 to the negative 11. You'll probably find you two-finger type it. You go 9, scientific notation button 9. Quick. Q1, 12, and then micro coulombs. Micro is 10 to the negative 6. 10 to the positive 6, that would be run away and pray to God. 1 coulomb would be a lot. 12 million boy. Like a lightning strike, Keegan, has maybe 30 coulombs, so 12 million coulombs. That would be on the order of about 1 million lightning strikes. Boy, you know what? I have to sit down and start running some numbers because I'm trying to figure out what would have that big a charge. I think the sun would have that many coulombs of I don't even know. So negative 6. Be afraid, dude. Nick, keep going. What's R? Don't say 0.75. That's a common silly mistake. Nick, look up. It's actually on the diagram. Ready? Where's Q1? Right there. Where's P? Right there. Please don't tell me this distance is 0.75. What is that distance? Help me out, Keegan. You're way overcomplicating it. Yeah. Okay. That's a small mistake that drives me cray-cray, and I will, because to try and give you like I could have given you, Nick, this distance and that distance, it clutters up the diagram. So typically I'll give it to you in chunks, and I'll expect that you're clever enough, which you were eventually, to figure out, I'm going to have to add some numbers together or subtract some numbers to figure out what R I want. What is 0.75 times 0.8, Keegan? Oh, I thought you were crunching it already. 1 point what? Squared. All right. What do we get? All of you, again, want to practice typing these in. I got kind of a yucky number. 44,953? Is that my final answer? No, I'm going to carry the extra sig figs. All right, 44,953. And I think I told you yesterday, newtons per coulomb. Typically, electric fields are in the thousands, tens of thousands, or hundreds of thousands. Coulombs, no. Electric fields, yes. Direction. So, Nick, what we're going to do is we're going to imagine this charge doesn't exist. This charge doesn't exist. What direction is the electric field from that guy? How do we figure out the direction? We're imagining a tiny positive test charge right there. How tiny? So tiny that it doesn't have its own electric field, because that would change the question. Which way would a positive sitting right there want to move because of Q1? Would it get attracted toward or repelled away, and why? Why? Because like charges. So let's call that, you could call it north, south, east, west. My default, I usually just go, I'll call it right. Okay. Are we done? No, repeat. Now, the nice thing is, once you've typed this in once, you can probably backspace and just edit and change a few numbers. In fact, I'm not going to rewrite the original equation. I'm just going to go straight to numbers. It's going to be 9 times 10 to the 9th. What was Q2? 8 microcoulombs. And what's R2? I guess 0.8 squared. So Keegan, I'm just going to backspace and edit. I need to change the 12 to an 8. And I need to change the 1.55 to a 0.80. 112,500? Does that make sense? Should it be bigger? Yeah, this charge is closer. Smaller charge, but way closer. That squared has a big effect. Direction. Electric field number 3. It's going to be 9 times 10 to the 9th. What was charge 3? 15 times 10 to the negative 6. All over 1.2 squared. Again, I should be able to backspace, edit, and insert. So 15 times 10, and then 1.20 squared. 93,750. Newtons per Coulomb. Direction. Which way would a positive at location P feel a force because of charge 3? Looking at our 3 numbers, which direction does it appear is winning? So we'll make that positive. So now on my calculator, I'll end up going winner 1112,500 plus winner 44,953 minus loser 93,750. Right plus right minus left. And I get 63,700. So the net electric field is, what did I say? 63,700 newtons per Coulomb. Direction?
Right.
Right. I won't give you on a quiz or a test a question that asks you to find 4 overlapping fields. In fact, I don't even think I'll do 3 overlapping fields. I'm going to pretend, Sarah, if you can do 2, you can do 20. It would just take longer. So I'm not going to worry about that too much. So here's our summary. Oh, was there a part B? There wasn't a part B, was there? No. Okay. The electric field can be found using, first of all, the definition if we're told the force on a test charge. In other words, I can find the electric field if you tell me how much electric force at a charge at a location is. That's the same, by the way, as little g equals Fg over m. If the obvious one is mg and you want to get the little g by itself, divide by the mass. Alex, this is why I've been saying Q, charge, behaves an awful lot like mass. Okay. We can also find it using the point charge equation if we're told the planetary charge that's causing the electric field and how far away we are. That's the one that we just used. Electric field is equal to K big Q over R squared. Just going to compare that with little g equals big G, big M over R squared. And Mallory, again, they look I hope, kind of similar. Big G is the constant to get kilograms and meters squared into newtons, well, into meters per second squared or newtons per kilogram. Little k is the constant to give us newtons per coulomb from coulombs and meters per second squared. Okay. Now, what else does that mean? In the same way, when I said to you last year, get the obvious one. What did I said, get the obvious one? Which force did I mean? Do you remember? Okay, in the same way, the shortcut for finding the force of gravity was mg. We have a shortcut here. First of all, we can, recall the direction is found by considering a positive test charge. It's away from a positive. It's toward a negative. It's which way would a positive want to move at that location if it could. What about finding the force? We can find the force between two charges using Coulomb's law. This is what I'm going to use if I have two charges, Q1, Q2, over r squared. And again, I'm going to argue this looks an awful lot like Fg equals big G m1 m2 over r squared. When would I use that? Well, if they ask me to find an electric force and they give me two charges and the distance between them. But you'll notice last year, Cohen, when we found gravity, we said, get the obvious one. We wrote this as our shortcut. I can do something similar for electric force. Cohen, get the Fe by itself. How would I move the Q over? If you happen to know the electric field at a location and the charge at that location, hey, you can find the electric force in the same way you could find gravitational force, because that little g contains that big monstrous expression. This little e contains that big electric field expression. When would I use that? The question would say something like a charge of blah, blah, blah is feeling a force of blah, blah, blah. What's the electric field? Or a charge is placed, a classic one would be an electron is placed in an electric field of magnitude blah, blah, blah. What force will the electron feel? You'll have to realize that you know the charge on electron. It's an electron. It's 1.6 times 10 to the negative 19. Positive or negative. Oh, we don't put the positive or negative into here. So remember, the direction of the electric force is found by considering whether charges attract or repel. Like charges, unlike charges attract. The direction of electric field is which way would a positive want to move if it could. Because they're both vectors, if we have several charges, we'll need to add them vectorially. If they're in a straight line with each other, winner minus loser. What if they're not in a straight line with each other? How do I add two vectors together? Okay. And then I talked to you yesterday about the most addictive bonus video game ever. Here's your homework. You can try number 1. You can try number 3. 6 is good. So far I've assigned 1, 3, and 6. I think I've told you these notes were originally typed in Word 95 for Mac. What year are we right now? The graphics are going glitchy, and so you'll see every so often what happened here is the micro symbol just wouldn't work anymore, so I typed it out. I'm slowly repairing these, but I'm hoping I don't have to redo all these graphics before I retire, because it's thousands of hours. So if you're not sure of a question because it didn't print quite right, let me know. They're deteriorating more and more every Windows update that comes along, so we'll see. Number 6 is good. Okay. Before you turn the page, Zaina, this is going to be a job for a free body diagram. What are the forces acting on this charge? It looks like gravity is pulling it down and electric force is pushing it up. Since it's at rest, you can say they're equal. You can say electric force equals little mg. Oh no, it's not at rest. You know what? One of them is going to be winning because it's asking you to find a speed. There's an acceleration. So try that one. I haven't done one like that with you. It's physics 11 plus physics 12. 11 is good. 13 is good. So I have not done one yet where you add them tip to tail. Try that. So find the electric field at location X. You'll have to add those two electric fields tip to tail, and then the magnitude will be Pythagoras, and then the what of what will be shift sine or shift tan or shift cos. North of south, east of west, what of what. It's doing nano charges, nano coulombs. Nano's 10 to the negative 9. I'm not going to give you 16. That's yucky. I like 17. And you can try number 19. And then you can also, in your spare time, Google FET electric field hockey. If you complete level 2, that will get you 1 bonus mark. If you complete level 3 without banking it off the screen by making the charge go through the obstacle course, that will get you 2 bonus marks. But you can't get 3 bonus marks. You can get a total maximum of 2 bonus marks on your test. There's about 40 minutes left. Can you all look at the ultimate review, please, that I gave you yesterday? If you want to get a head start, now, I would love to, I don't think it's going to happen, I would love to get this test in next week, Thursday, before Christmas. That would be better, I think. I think to do that, I'd really have to crack the whip. So it's probably going to be after Christmas. Keegan, just hang on 1 second. You got any tissue? Okay. But to get a head start on the ultimate review, you can already do number 2. You can circle that one as one you now know how to do. Number 5. You can do number 10. Number 10 is a bit nasty. I'll put a star next to it. My answer key is online. It's just asking you for the direction of the force, not the magnitude. So you'll use like charges repel, unlike charges attract, and you'll have to look at the setup and figure out which forces are stronger, which ones look like they're weaker based on their distances. Okay? You can try number 11, but it's also tricky. I haven't done one like that with you. There's going to be something like number 12 on your test. Here's an example, and because it takes a fair bit of writing, it'll probably be worth 7 marks. Finding an overlapping electric field. You can totally do that one. You can totally do number 14, finding an overlapping electric field, and you're going to start to notice a bit of a theme here as we do these electric fields. 17 is good, nice conceptual. (21) Here's an example of a charge diagram and how I could ask you a multiple choice question about it. Here, I've told you the polarities. I'm just asking which of those diagrams was done correctly. In which one do the arrows point the correct direction? Okay. 23 is good. Nope, never mind. I take that back. You don't know how to do potential yet. You will someday, potentially. 25 is good. 27 is tough. You can do it now, but look at my answer key. It's tough. Nope. 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 Here's a nice electric field lines picture. 33. $35 is doable. 36 is doable. I'm going to stop there, but if you finish the homework in class, you can start to whittle away at these a little bit so that it's not a complete stranger.